Hi there. Today we're looking at lesson 2. We're talking about properties of exponential functions and taking a look at some of the characteristics of exponential functions. We know the parent function for an exponential graph is y equals b to the x power. And when you stretch that graph, you need a stretch factor of a onto the parent function. So when the absolute value of a is greater than 1, you have a stretch. You have a shrink factor when you have a times b to the x power, and the absolute value of a is a number between 0 and 1. So we're talking about a fraction there, and that would be a compression. And you can reflect your graph across the x-axis when your a value is a negative number. And then if we want to translate by moving the graph to the left or right, up or down, then that's going to occur when you have some h and k value on the parent graph. When we have x minus h, that's a movement left or right, depending on the sign of the h value. And when you have a k value, positive or negative, that's a translation up and down. So h and k is like that starting location. And then putting all of those together, all the transformations combined, would be when we have a format or model of y equals a times b to the x minus h power plus k. The next characteristic of an exponential function is when we have a natural base. That's e to the x, and we know e is an irrational number. In other words, the decimal behind e to the first power does not stop. It continues to go 2.71828. It just keeps on going, similar to pi. Compound interest, continuous compound interest, that's the formula. Some amount is P to the RT. P is the principal, R is the rate, and T is some unit of time. And then our half-life formula, when we're talking about radioactive decay and bacteria growth and such, that's the amount final is equal to the amount initial times a half-life of T divided by K. And in the lesson, we'll see what those variables represent. So we want to first graph a few graphs, and we want to look at the parent graph of y equals 2 to the x. So 2 to the negative 2 is 1/4, and 2 to the negative 1 is a half, and 2 to the 0, 2 to the 1, 2 to the 2, and so forth. So if we graph that graph, we're going to graph this graph in red. I'm going to put a little red star by there. 2 to the x. When x is negative 2, y is 1/4, and negative 1, it's 1/2. And 0, 1 is on our graph. 1, 2. 2, 4. If we kept going, 3 would be, 2 to the 3 would be 8, and 2 to the 4 would be 16. So we could get that parent graph going along as exponential growth like such. So this is our parent function, and its hk value is 0, 1. Then if we graph y equals negative 1/2 times 2 to the x, so we're cutting the graph 2 to the x. You notice we're doing this. We have this compression, and then we have a reflection over the x-axis. So filling in that table for us, we have negative 1/2, negative 1/4, negative 1/2 again, negative 1, negative 2. We got a mistake here. Let's go fix that. That should be negative 1/8, not negative 1/2, because I'm multiplying 1/4 times negative 1/2. So now when x is negative 2, y is negative 1/8. when x is -1, y is -1/4. When x is 0, y is -1/2. When x is 1, y is -1. When x is 2, y is -2. And then when x is 3, we're cutting 8 in half, so -4. When x is 4, we're cutting 16 in half, -8. So here we have this graph. It has a compression factor of 1/2, and it has a reflection across the x-axis because of the negative on the a value. And our HK number is 0, -1/2 in this case right there. So if we want to describe what happens and compare that graph, we could say the a value is -1/2. That a value reflects our graph, reflects the parent graph y values over the x-axis, and it also acts as a shrinking factor, and it shrinks our parent graph by 1/2. In example 2, we're going to graph y equals 3 to the x, so 3 to the -2 power is 1/9. 3 to the -1 power is 1/3. 3 to the 0, 3 to the 1, and 3 squared. Now, when we move this graph over 3 to the -2 plus 1, that gives us 3 to the 0, so we have 1, and then 3, and then 9, and then 27, and then we're off the chart at 81. So I want to graph the parent graph 3 to the x. I'm doing that in red. And -2, -1, 0, 1, 1, 3, 2, 9. So our parent graph is here in red. The HK value is 0, 1. That's this point here, 0, 1. And then in blue, we'll graph our translated graph. So what's going to happen? We have -2, 1, -1, 3, 2, 0, 9, and 1, 27. So we're off the chart way up here somewhere. So this graph is our translated graph. And 0, 9 is our new y-intercept. And how did that compare to our parent graph? Well, we know that the x plus 2 value translates each x value, each x value of the parent two units left, 2 units left. So this red point at 0, 1 moved over here. This one at 1, 3 moved over to -1, 3. And the one at 2, 9 moved over to 0, 9. So the x values in each case changed, where this one was 2, 9. This one became 0, 9. For example 3, we want to graph with a graphing calculator. And I want to graph y equals 1/2 x as my parent graph, 1/2 to the x power. I'm going to graph that in red. So we have 0, 1, and -1, 2, and -2, 4, and -3, is at 8. And then we know at 1 we have a half, and so on. So we have this exponential decay, which is our parent function, 1/2 to the x power, with this point 0, 1. And if we analyze that, we know it's a decay function. We know that 0, 1 is the y-intercept. We know the domain is still all real numbers. The range is all the values above the y-axis, the x-axis, and we know that y equals 0 is the horizontal asymptote. Okay? So nothing's going to go below y equals 0. AS, so you got to spell here right. ASY MPTOTE. Now, switching over to blue, we're going to graph our translated graph with the 3 and the 1/2 to the x power plus 2. So we still have the HK, but we've got that factor of 3 in front. So this is going to stretch our graph, and this is going to move our point up 2 places. So it's a decay question. It's a decay graph. And instead of having 0, 1, we have 0, 5. Because we had 1 times 3. So we're having this 1 here times our stretch factor 3 and adding 2, which gives us 0, 5 for our y-intercept. And the domain is still going to be all real numbers, but the range would be everything greater than this k value. This is going to create my horizontal asymptote. So we're going to have everything above 2, or if you want to write it in interval notation, from 2 to infinity. And we know that y equals 2 is our horizontal asymptote. And we know that we have an a value of 3, which is a stretch factor. So a equals 3 stretches our functions, the red parent function. So 0, 5 is our y-intercept. When x is -1, y is 8. And we have a vertical break at 2. A horizontal break at 2. So this graph is going to come down here like this. And it won't go beyond y equals 2. 0, 5. And like I said, you can check that using your calculator and verify that we have a graph that looks like this and a graph that looks like this based on the parent and our translated graph. In example 4, we want the best temperature for brewing coffee we know is between 195 and 205 degrees. So coffee is cool enough to drink when it's about 185 degrees. We want to use the table below to write an exponential model and find how long it takes for the coffee to reach a temperature of 100 degrees. Okay, so the first thing I want to talk about is I'm going to be using a TI-84. So I want to enter the data in my TI-84, and the way I can do that is I'm going to look for the stat key and then hit the edit key and hit list 1. And then in list 1, we're going to list all of these values from 0 to 30. And then I'm going to use list 2. I would repeat that step in list 2. I'm going to enter these items into list 2. So list 1 and list 2. And then after we get all of that done, the next thing we want to do is we want to view the scatter plot. Now, if you have an Inspire, the directions are a little bit different. But to view the scatter plot, I would hit the second button, and then I would hit the y equals key, and then I would hit the number 1. And by doing that, when I hit the number 1, I want to turn that plot to on. And then to look at it, we want to hit the zoom key and the number 9. And then we would see the scatter plot. Next, you can find the exponential regression equation. So we want to find exponential regression. And we're going to let the calculator write that equation for us. And the way to get that exponential regression equation is to hit the stat button, the calculate button or choice, and then the number 0. And we want to do vars, and then the y vars, and then 1, and then 1 again, and then enter, and then enter again. And that way it will do all the calculations for us. And our equation is going to be y equals 201.719 0.9770 to the x power. And if you look at the equation at about 30.2 minutes, you'll see that the temperature is right around 100 degrees. And that's what they were looking for. When does that coffee cool off to 100 degrees? So it's right about 30 minutes. In example 5, we're going to use the calculator to evaluate e to the 4th. And I get about 54.598. E to the negative 2 power is the same thing as 1 divided by e to the positive 2. And that's about 135 behind the decimal. E, the square root of e cubed is about 4 and 482 behind the decimal, or 482 thousandths. And e to the 2/3 is 1 and 948 thousandths. Then our very last example is, no, we got 2 more examples, I'm sorry. In this, the half-life problem, here's where our formula from the first page of notes, where each variable is defined. And we want to use this equation, our half-life equation formula. We have a certain radioactive element has a half-life of 250 years. So that's our K value. We know K is 250. So K is 250. If there's 42 grams, so our A value, our A sub naught, is 42 grams. How many grams will remain after 462 years? That's our time. So 462. And we are going to use A sub final is A sub naught, which is 42, times 1/2 to the 462 divided by 250. And we're looking for that final amount. So 42 times 1/2, and I'm going to break this down to 1.848. So doing that calculation, 42 times 1/2 to the 1.848 power is about 11 66/100ths of a gram would remain after 462 years. Then our PERT formula, that's a famous formula for finding continuously compounded interest, compounded every second. So A is our amount at some time t, P is our initial investment or principal amount, R is the annual interest rate written as a percentage, and T is for the time in years. So let's say in example 7, suppose you have won a contest at the start of the 9th grade and you deposited $4,000 into an account that pays you 5% annual interest, compounded continuously. So now I know I need this formula here. How much will be in the account when you enter college 4 years later? So we know that we're looking for the amount at the end. Our principal investment was $4,000. The rate was 5%, so 5 divided by 100 is 0, 5 behind the decimal, and the time is going to be 4 years when you leave to go to college. So the amount in 4 years from your $4,000 investment, that's your P, E, R, and T. So you're going to calculate on your calculator 4,000 e to the 0.2 power, which turns out to be about $4,885.61. So if you didn't touch that money at 5%, you'd have really close to $5,000 when you got ready to go to college. Maybe you could buy your books for that 4 years of college with that money. See you next time.